Thanks for coming to the presentation. The topic of my presentation is Mixup Augmentation for Generalizable Speech Separation, which is a paper accepted at MMSP. The authors of the paper are myself, Lin Wong, Paulo Gastaldo, and Andrea Cavallaro. I'll start by introducing the problem of speech separation in noisy environments. Speech separation in noisy environment is separating mixed speech signal into speaker signals of its constituents in presence of noise, and applications of the system include hearing aids, capturing and transcription of YouTube videos, human robotic interaction, and automatic speech recognition. The main motivation of this research is to improve the generalization of separation models across datasets and to improve separation performance in unseen noisy conditions. Traditional regularization techniques such as dropout, early stopping, and even other augmentation techniques such as SpecAugment do not seem to improve the generalization performance, as we will see in the experiments later on. The main contribution of this research work is that we extended mix-up augmentation and its variants for time domain speech separation, and the proposed data-only mix-up improves inter-corpus speech separation performance. I will start by briefly discussing the separation model architecture that we're using. We're using DPRNN model. So DPRNN model is an encoder masker decoder time domain model. And the encoder is a 1D convolutional network which takes the input mixture as its input, and we get a 2D representation from it. And this 2D representation is passed to the masker network to generate individual mask for each speaker. And this mask is multiplied with the learned representation and fed to the decoder, which is a 1D transpose convolutional network to get the predicted sources in the mixture. Going towards mix-up is mixing two distinct mixtures from a mini batch. So here XIB and XJB are mixed with a mixing factor of 1 lambda and 1 minus lambda, where lambda is drawn from a beta distribution parameterized by alpha and beta. And similarly, we mix the sources as well, as you can see in the figure. Going towards variants proposed in this work, firstly, we have complete mix-up. Complete mix-up is training using mix-up augmentation for all the epochs until Emax epochs, and partial mix-up where we have regular training until early epochs, and followed by mix-up training for every Q epochs. Next is pre-trained mix-up, where we do regular training until Emax epochs, and then fine-tune the pre-trained model using mix-up augmentation until EBT epochs. And finally, data-only mix-up, where we apply the mix-up augmentations only on mixture and keep the ground truth as the most dominant source in the mix-up augmented mixture. Going towards experiments and for one TIMIT dataset, here the important thing to note is that the noise corpus used in LibriMix and VCTK datasets are the same, which is the WAM noise corpus, and in the TIMIT dataset we have a completely different noise corpus, which is environment noise corpus. And for experiments, we have two sets of experiments. First one is Intra corpus, which is training on LibriMix train 100 split and testing on test set of LibriMix dataset, and intercorpus, which is training on LibriMix train 100 split and testing on TIMIT test set and VCTK test set. Going towards the ablation of scalars or mix-up. So as I had stated previously, we use a lambda mixing factor, which is drawn from a beta distribution parameterized by alpha and beta. And we try to find out the best values of alpha and beta using grid search with 3 different values using two distinct variations of mix-up, which are complete and data-only mix-up. And as we can see the results in the table, we get the best results from alpha value of 8 and beta value of 1 for both these variants. Which going towards intra-corpus results. So these are, to reiterate, this is the results from training on LibriMix train 100 set and testing on LibriMix data set. As we can see, none of the augmented models significantly outperform the non-augmented model, and especially frequency masking has the worst performance in our case for SpecAugment, and rest all the augmentations have comparable performance to the non-augmented model for intra-corpus experiment. For intercorpus experiment, which is training the model on LibriMix train 100 set and testing it on TIMIT dataset. So here we have 6 sets of mixtures, which are ranging from -5 to 20 dB, -5 being the most noisier one, most noisy mixture, and 20 being the least noisy mixture. So as we can see, it's clear that separating a noisy mixture is significantly harder than separating a clean mixture which doesn't have noise. And we can see from the results that a data-only mixer performs the best, which is roughly 1.4 dB performance improvement as compared to the non-augmented model. And also, it's important to note that TIMIT dataset has noise types are different from LibriMix dataset, which is trained on, so which also shows improved generalizability of from using data-only mixup. Next, we'll go for we'll look at intra-corpus results using VCTK dataset. So here, similar to the table that we had previously seen, data-only mixup performs the best, but we can notice that the performance improvement in case of data-only mixup is not as substantial as what we had seen in the previous experiment with TIMIT dataset. So we attribute this to the fact that both TIMIT and both VCTK and LibriMix dataset has the same noise corpus, and thus the performance improvement not being that substantial. And to conclude, data-only mixup improves the cross-corpus performance from speech separation model. And also, additionally, it's important to know that data augmentation approach doesn't incur any additional network parameters, and thus doesn't increase the training time. And also, future work would include finding optimal augmentation combinations using a learned augmentation strategy such as auto-augment and augments. Thank you.